Okay, so we learned lattice path and Q binomial coefficient and Parker-Hammer symbol like that. And the important thing is this: the generating function for partitions inside this rectangle is given by Q binomial coefficient. This will be very important. And it's called Q binomial coefficient. And from that, you may guess that there is something like Q binomial theorem. And it is true. Binomial theorem is a theorem about expanding 1 plus x to the n. And it is, in its expansion, we have binomial coefficient in x to the k power. All right? So recall 1 plus x to the n is equal to k from 0 to n to the k, x to the k. So this is the binomial coefficient. And this is the reason why it's called the binomial coefficient. It is a coefficient, and it's binomial in this binomial expansion. We have Q version of this. It's called Q binomial theorem. Very useful theorem in Q series. 1 plus x q dot 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 1 plus x q to the n minus 1. Okay. They are equivalent, but let me write this way. Yeah, let's start with 1. Okay, 1 plus x q squared, like that. Yeah, it's possible that we can go from 1 plus x, but yeah, they are more or less the same. So this is equal to k from 0 to n, and choose k sub q, q to the k plus 1, choose 2, x to the k. So this is the theorem. All right, so do you see this is a generalization of this? Usually Q something means if Q equals 1, we get the original one. This kind of theorem is called Q analog. So basically we have 이거 아직도 켜져 있는 것 같은데? 그래요? 추워지네요. Okay. So this kind of theorem is called the Q analog. Q analog of this. That means it is a general version. We have Q inside. But if Q equals 1, we get the original one. If this happens, it's usually called a Q analog of something. So this Q analog of binomial theorem. That's why it's called Q binomial theorem. If Q equals 1, we get the usual binomial coefficient back, right? This part is just everything is 1 plus x if Q equals 1. So 1 plus x to the n, right-hand side, left-hand side. Right-hand side, this is just 1. This is binomial coefficient, so we get this. So it is a generalization of binomial theorem, Q analog. Let's prove this. We have all the ingredients to prove this. Left-hand side, just try to expand this and see what happens. So when you expand the product of polynomials, what do you do? What do you do? In each factor, you select one term, right? And then you multiply them. That will give you one single term in the expansion. So in fact, there are two choices for this, two choices for this. So in fact, simply selecting this, you will get 2 to the n terms. But of course, some of them will be simplified by if you have the same Same thing. But basically, we have 2 to the n choices. So, let me write this way. Lambda, that one expansion like that corresponds to making one partition. So one term in that expansion, one term corresponds to one partition like this. So distinct partition with largest, just to say parts. Each part less than equal to n. Let me write and explain. I claim that left-hand side is equal to this. Why? Because selecting. So imagine the ith term, ith vector, 1 plus x times q to the I, right? You have 2 choices. Either you select 1, so okay, let's put it this way. In this ith vector, 1 plus x q to the I, selecting, we have to select either 1 or x q to the I. Selecting this term x q to the I corresponds to having this part I in lambda. Okay? So example, let me example. 1 plus xq, 1 plus xq squared, 1 plus x. Okay, yeah, because we need more space. I'm going to explain this in this case, the next page. So example, 1 plus xq, 1 plus xq squared, 1 plus xq cubed. Let's think about this. So suppose you select this, and here this, and here say this. That should appear in your expansion. So like 1 times xq times q squared times xq cubed. I'm gonna say, okay, I'm gonna make a partition lambda. So here, did I select xq? No. So 1 is not there. I selected 2, this vector, that means we must have 2. I selected this, 3. It's like that. This corresponds to this. So each vector, in each term in your expansion will give you exactly 1 partition. That's why we have that claim. Is that clear to you? And if you have this, what is the coefficient? What is the power of x? Whenever you have 1 apart, you will get x vector. Whenever you have a part equal to I, you will get q to the I. So if this corresponds to this must be equal to x to the length of lambda, number of parts, q to the size of this, like this. Here q to the 3 plus 2 x squared, in this case. X squared, q 3 plus 2. So expansion is exactly the same as making 1 partition. That's why this is true. Is this clear to you? So this is the explanation for this, an example. All right, now what? And the parts must be all distinct because you cannot select this twice. This is the only time you can select this. But instead of doing distinct part, we want to have just the usual partition without this condition. So when we have this, number of parts is, let's say, k. Oh, okay. Let me rewrite this. The number of parts. What is the maximum number of parts here? N. Because each part must be less than or equal to n, but you can get that only by selecting these. But anyway, so if k is the number of parts, k goes from 0 to n, x to k, now we get this. Lambda is a distinct partition, but it has exactly k parts, so we may write this way. So lambda 1 less than k, less than n. So we can rewrite this in this way, by collecting the partitions with the same number of parts, k. I just rewrote this sum. It has k parts, all distinct, positive integers, less than equal to n. Alright? Now I'm going to rewrite this one more time so that we can get Q binomial coefficient. So if we don't have this condition like, oh yeah, distinct, I forgot to say distinct. If you don't have this, this is easy. We know this. But Q binomial, it is a partition inside a rectangle, something like that. So we want to remove this condition. We can do that always, like by defining mu this way. Mu1, mu k, where mu k, mu I is equal to lambda I plus. Basically, the idea is here you take minus 1, minus 2, dot, 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 minus k plus 1. So I minus 1. I plus 1. No. K minus I. Minus k plus I, yeah. No. Let me wait. Okay, I'm not going to say this. This is equal to this minus k plus 1. This is equal to this minus k plus 2, etc. You see what I mean? If you really want, you can say, okay, mu I is, what is lambda I? Oh, I see where I made mistake. Yeah. Plus 1 minus I. Yeah, the mistake that I made is this must be minus k. If this is minus 1, right? Is it okay? So basically you subtract minus 1 to the last one, minus 2 to the second last, etc. So k, this is equal to k. Alright. Sorry about that. Minus I. Plus I, plus I. Alright. Yeah. If k equals, I equals 1, we get minus k. I equals k, we get minus 1. So yeah, I think it's okay now. But anyway, the idea is you subtract these numbers increasing way so that this will have no longer this condition, distinct. And what is the condition here? The mu1 greater than mu2, we don't have strict inequality. Mu k, now it can be 0 now. And what is the maximum value of possible value for mu1? N minus k, yes. So this, now what is the cardinality or size of lambda and mu in comparison? This plus 1 plus 2 plus dot 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 k, which is k plus 1 choose 2. This is the sum of integers 1 through k. This is one-to-one correspondence, and you can rewrite this in this way. Instead of lambda summing over lambda, mu, but now mu is a subset of this partition. The largest part is n minus k, and we have k parts. Where 0, we may have 0 parts. So in other words, mu is a partition inside this. N minus k, k. Any partition. And q to the k plus 1 choose 2 plus mu. Alright? Now we are almost done. This is constant. This part gives you this. And what is the sum over all this part? What is this part? The binomial coefficient, Q binomial coefficient. Because we sum over all partitions inside this rectangle, which gives you this. This plus this and K for this. So that's the proof. So this is a standard technique, changing partitions of distinct parts into two partitions without the condition that they are distinct. So this is Q binomial theorem. This is very useful, and it will be used many times. And there is another version of this Q binomial theorem, and that is one of the homework problems. Question? All right, now I'm going to move on to the next section about inversions. Actually, we defined this before, but let me recall you. We have a permutation, pi 1 dot 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 pi n. Then we say that I comma j, this pair, is an inversion of pi if I must be less than j, but pi I is greater than pi j. So the ith position and jth position, their orders are reversed. The first, they are out of order. The bigger number appears first, then it's going to be, that pair is going to be called an inversion. And this notation, I of pi, or I also write inv of pi, is the number of inversions of pi. We learned this when we define the determinant. And the sign of a permutation is defined to be -1 to the number of inversions. All right, remember? Inversion. And proposition. Sum over all permutations Sn, Q to the number of inversions, is equal to NQ factorial. So this is another Q analog. Q analog of the fact that the number of permutations of Sn is equal to n factorial, right? We know that the cardinality of Sn is equal to n factorial. Number of n factorial. The number of permutations is n factorial. This is a Q analog of this, because if Q equals 1, this reduces to this. But it also has very nice. So usually Q analog has this kind of property, very nice product. Or if you want, you can write this in this way. Q dot dot dot. Let me erase this part now. Dot dot dot. 1 plus Q to the n minus 1. We have n. Oh yeah, we have 1 over here. Including this, we have n factors. So we are going to prove this now. Proof is not that difficult. For pi permutation, define, say, the inversion sequence of pi by like this. Let's say IS for inversion sequence. It's a sequence A1, A2 dot 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 AN such that AK is equal to the number of pairs pi I comma pi j such that they're inversion I less than j, pi I greater than pi j. That means I comma j is an inversion, but yeah, rather than I comma j, I'm gonna focus on this. And pi I equals k. What does that mean? So in other words, this is in this way you can think of this way. Number of inversions say caused by k, something like that. Or this is the, in other words, number of pairs j such that j k in pi j greater than k, and oh yeah, I think this is k, j, pi j. Is that right? Oh, I think I have a typo in my lecture note. But anyway, this is what I meant. Yeah. So basically we count integers greater than k but which appear earlier than k. This will give you one inversion, right? So I'm going to count that number, AK. And if you make a sequence using AK, that's going to be the inversion sequence. Let me give you an example in the next page. Example. This should make this clear. 7, 2, 4, 1, 6, 5, 9, 3, 8. Okay? So what is the inversion sequence of pi? Let me write the sequence. Okay. Let me write their positions just for convenience. So A1. How many integers are to the left? How many integers which are bigger than 1 and which are also to the left of 1? There's nothing. Actually, this is always 0. How many integers are there to the left of 2 greater than 2? Wait. Sorry about that. Actually, there are many ways to do this, but I think I... Okay. Yeah. This is not what I meant. This is right. This is right. So, sorry about that. Number of j such that in pi we have j appearing earlier than k. Oh, no. Later than k. While k is greater than j. This is what I meant. Yeah, you can reverse the order, but yeah. Yes, let me just stick to this notation. So, okay, yeah, this is always 0. You look at the left parts of 2. The things which are to the right of 2. How many integers are smaller than 2? 1, right? So this is an inversion, so 1. 3. How many integers smaller than 3 to the right of 3? 0. And 4. How many integers are smaller than 4 and to the left of 4? 1 and 3. So basically you count just the inversions caused by this. So 1, 2. It's like that. 5. Smaller than 5 to the left, to the right of 5? 3. Just 1. And 6? 1, 2. For 7? 1, 2, 3, 4, 5, 6. For 8? Nothing. For 9? 2. So we have 2. So this is the inversion table. And what is the condition for AI? How many integers are smaller than I in total? I minus 1. So the maximum value would be I minus 1. Smallest value, of course, 0. It always satisfies this. And for any sequence satisfying this, you get the permutation back. This is, in fact, a one-to-one correspondence. This has enough information to reconstruct your permutation. If you know these inversion tables, you can reconstruct. How? So suppose that we don't know this. Let's pretend that we don't know this and try to reconstruct this. One is reconstruct integers, smallest integers, one at a time. Two must be either this side or this side. But because of this, where is 2? Here or here? Should be to the left. Because if this is here, this must be 0. Because of this tells you this. Basically, this number tells you which position 3 goes. 3 goes here, here, or here. 0 means you have to go this way. 4 has to go to one of these. 1, 2, 3, 4. Which part? 2. Because we want to have 2 inversions caused by 4. And what about 5? You want to have only 1 inversion, must be here. In this way, you can construct everything. This has enough information. It is indeed a bijection. For any sequence satisfying this, you can get this. Because this just tells you which position you put this number I. So, this is it. By this is an permutation. So IS is a map from set of permutations to, let's say, 0, 1. Here, this means the set of integers from. Okay, yeah, this is not a standard notation. Let's use just a curly brace. In your sequence, ith position, you may have 0, 1, 2, up to I minus 1. This is a bijection. One bijection, as we saw before. And if, moreover, if is of pi equals a1 dot 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 ak an, what can you say about the number of inversions of pi? What is the number of inversions if this corresponds, if the inversion table is this? Can anyone tell me? A1 plus A2 plus just this. Each inversion will be counted exactly one of these. So this is almost, we are almost done. So left-hand side here is equal to, now instead of pi, we can use inversion table. A1 dot 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 an, where ai less than, greater than 0, less than I minus 1, q to the inversion is replaced by this. But now you can notice that these are independent of each other. AI can be selected just as you wish without considering other ij's. That means I goes from 1 to n. You can kind of factor this out. AI is from 0 to n minus 1, q to the AI. You just, because they are all independent. But this is nothing but n, oh no, I minus 1. This is nothing but I factorial. Oh no, I sub q, so it's n factorial. That's the proof. Question? So the generating function for permutations. So people normally say this like this. Generating function for permutations according to the inversion statistic is equal to nq factorial. Generating function, this statistic. Usually statistic in combinatorics, statistic means a function from some combinatorial object to numbers. All right, okay. So this is for just a usual permutation. In permutations with distinct integers, 1 up to n. But we can also consider permutations of multiset. So in a set, we don't have any repetition. Either this element is there or not. We don't really consider the multiplicity. How many i's in the set, we don't really care. If it is either there or not. But in multiset, we will also consider multiplicities. It's also using just this same notation. So if I write like this, it means a multiset where we have A1 ones, A2 twos, etc. We consider the multiplicities as well. It's a multiset. It's a common notation for the multiset. Okay? And S of M is the set of all permutations of M, elements in M. So example, S, if your multiset is 1, 1, 2, we have two ones, 1, 2. Then it's going to be 1, 1, 2 or 1, 2, 1, 2, 1, 1. It's like that. So it's a set of all permutations of multiset. Okay? Yes. Proposition, very simple proposition. Number of elements or number of permutations of these, I think you also learned this in your high school. How many elements are there? Remember? A1 plus dot 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 an factorial divided by A1 factorial dot 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 an factorial. Probably you have computed like what is the past mathematics? How many permutations of the letters of mathematics are there? You just pretend that they are all distinct, like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 letters. I think too many. 11 factorial. But these two m's, they are really the same, so permuting them doesn't give you anything different, so you divide this by 2 because there are two m's, and there are two a's, so you divide this by 2 factorial. There are two t's, divide by 2 factorial, like that, you remember? It is, yeah, it can be proved like that. Just assume that they are all distinct, but then you divide this by this number. Because these kind of permutations of the same letters give you the same thing. So this is a very well-known and easy fact. And this is commonly denoted this way, A1 plus dot 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 AN, A1 comma dot 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 AN. It's called a multinomial coefficient. This is a generalization of binomial coefficient, multinomial coefficient. Okay? And the reason why this is called the multinomial coefficient is that, note, we have a theorem like multinomial theorem. If you expand this multinomial like this, like m, then this is going to be equal to I1 dot 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 ik. Oh yeah, their sum is k. Oh no, I'll rewrite this. I1 plus dot 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 in equals m multinomial m I1 dot 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 in x1 to the I1. So this is called the multinomial theorem, which can be proved same way like a binomial coefficient theorem. Now this is why it's called multinomial coefficient. It is coefficient of this expansion. Okay, we know the cardinality, but we will prove more than this. Definition. So again, let's say M is this. And for convenience, let me define their sum. And let's say pi is a permutation of these elements. So you must have m elements like this, S of m. This is a permutation of these letters. And we can also define inversion of this. So I comma j is an inversion of pi if, again, I less than j, pi I greater than pi j. And I of pi is the number of inversions of pi. So for example, if pi is 1, 3, say 2, 1, 2, what is the inversion number? You count pairs which are out of order. 1 it's always okay. 3, 2, 3, 2, 3, 1, 3, 2, and 2, 1, right? There are 4 inversions, so it's going to be 4. Like purchase permutation. And we're going to define Q multinomial coefficient. It's called Q multinomial the same way. A1 plus dot 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 AN is equal to A1 plus dot 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 AN. Just the same way defined. It's defined the same way. And this is equivalent, just using the definition, like binomial coefficient. They are the same. So Q binomial theorem coefficient is a special case of this. And K can be written this way. K n minus K as a multinomial coefficient. And here, the sum of the integers in the bottom must be equal to the integer in the top. Again, it is not clear just from this definition whether this is a polynomial in Q. But it is a polynomial in Q. We will see in a moment. Okay, let's see the proof. Let's see what this represents. Proposition. M is this. Then the sum over all permutations of this multiset, Q to the inversion is equal to the Q binomial coefficient, Q multinomial coefficient. Yeah. So for simplicity, let me define M to be the sum of them, AI, sum of the AIs. Proof. By the way, this is a generalization of permutation, right? Permutation, in the sum of this over permutation, we obtained n factorial, nq factorial. Do you see that from this proposition? If these numbers are all 1, then we will get simply just permutation, usual permutation. Then here what happens? Something m choose 1, 1, 1, 1, 1 in the bottom. You get just n factorial. So it is a it gives you that theorem back. So it is a generalization. So whenever you see a generalization of this, try to check whether this gives you the special case, simply whether it simply reduces to the known fact. But it does in this case. So let's prove this. The proof is quite similar to the proof of these mathematics, rearrangements of the mathematics. Try to assume that they are all distinct. So idea is basically the same. Consider all elements in M are distinct. And then just proceed. Of course, we have to deal with the things that are the same. So let's define, because we have, for each I, we have AIIs, like in M, we have I, like I, AIIs. So just rename them like this, I1, I2, but just we need ordering of these letters because we are talking about inversions. A sub I. Let's rewrite this by putting subscripts. And just suppose that they're all distinct and in this order. Okay? And of course, we have to compare I, X, and J, Y's. Always, we can always respect the usual order like that. All right? And let's say A is this. So now A are a set of these letters. I from 1 to N, J from 1 to AI. So, meaning just replace all of these like this. Okay? Then, what happens is, what is the permutation of this? Permutation of the elements here. This is, let me write this way. This is almost identical with this. S of M times SA1 times ... SAN. Where we identify pi with, say, pi 0, pi 1, pi n, where, okay, what is this? Pi 0. Here, we have permutations of all these letters. I's are distinct, in that case. So just forget about the subscripts. This pi, how can I say, with every I sub j replaced by I, meaning we just forget about the subscripts. And ij, what is this? Pi I for I greater than 0. In this original permutation, we had permutation of these. that will record, that will be this one. So this is the permutation of the indices of pi, of I in pi. So let me give you an example. This will make this clear. So let's say pi is equal to 2, 1, 3, 1, 2, 2. I'm gonna need subscripts. 3, 1, 1, 2, 1, 2. Okay? So this is a permutation of these elements. They are all distinct. We assume that they are all distinct. What is pi 0 in this case? What is pi sub 0? Pi super 0. You just forget about these letters, subscripts. 2, 1, 3, 1, 2, 2. Is that right? And what is pi 1? You look at 1 and you just record the subscript. It's going to be 1, 2. Can you tell me what pi 2 is? What is this? Pi 2. Tell me. 3, 1, 2. Because you focus on the 2's and then you just record the subscript. 3, 1, 2. And pi of 3, pi sub super 3? Just 1. There's only one thing. Do you think this has enough information to reconstruct pi? Of course. And this is basically the idea of the proof of mathematics, rearrangement of the mathematics. You prove something like this. Your proof is identical to this. I just wrote this just like formally. So this is a bijection. So they are more or less the same. But under this bijection, what can you tell about the inversion number of pi? If this correspondence, if you have this correspondence. If you want to compute the number of inversions here, what is this? If just look at just these bigger numbers, big numbers, and then the inversions will be of the bigger numbers will be an inversion here. For instance, this and this, no matter what these numbers, the subscripts are, this is going to be an inversion. So we always have pi inversion of pi 0. But also, just look at this. This is an inversion, right? In pi. Because we assume that this is small law, this is second, the third one. This is an inversion. This is an inversion here too. So this, for the same letters, this is an inversion if and only if it is an inversion in pi I. So this is going to be equal to the sum of all of these. Is this okay? So this bijection is a very good one to keep track of the inversions. So we are almost done. So the thing is, the left-hand side was this. I of pi. But we have this one-to-one correspondence. Pi 0 in S, it must be A. Pi I in S sub AI q to the pi 0 plus dot 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 pi n. This is what we found, right? But now we know what this is. What is this? Here, they are all distinct. So it's just a permutation, usual permutation. So sum over all of this is equal to m factorial. And we assume that this is the sum of all i's. And here, let me rewrite the right-hand side. Let's keep this. So they are all separate, so we can write this way. As A1 dot 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 okay. But what is this? Again, it's just permutation. So A1 factorial. And this also ANQ factorial. So this is what we wanted to know. Now we have everything. So we just obtain that this is equal to this divided by this. That's the proof. So we just use the effect on permutations to obtain the fact on the permutations of multiset. Any question about this proof? All right, now we know this. We're gonna give another proof of the Q binomial coefficient being the generating function for partitions. So recall, we had this. Partition inside a rectangle is the binomial coefficient. Let's prove this. Actually, this can be rewritten in terms of binomial binary sequence. So lambda can be considered as a binary sequence. Binary sequence means a permutation of zeros and ones. Say pi, S of 0 and 1m is multiset. So example, so if permutation is like this, this is a partition. You look at this part, right? This is your partition lambda. And I'm gonna, we have this correspondence. If you go up, we write 0, 0, 1, 1, 0, 1, 0, 1, 1, 1, 0. So this corresponds to permutation pi, 0, 1, 1, 0, 1, 0, 1, 1, 1, 0. Now, what is, so here we consider lambda, the size of lambda. What is the size of lambda here? It is the number of inversions in pi, because this counts the number of cells inside of this, in the upper part of this path. For instance, let's look at this. This corresponds to one inversion. If you look at the column and row containing this thing, look at this. The 1, 2, 3, third one, 3 in the position 3. 1, 2, 3, 4, 5, 6. This thing. This is an inversion, right? For each inversion, you get one cell here. That exactly corresponds to this thing. This is the correct. This is the proof of this. One cell here is one cell corresponds to one inversion. Exactly. That gives you this fact. Is it clear to you, this correspondence? So just look at anything. Just for instance, what about this? Look at this part, and this over here is going to be this and this. So this and this. Again, inversion corresponding to this cell. For every cell, you can find one inversion. So this thing, summation lambda inside a rectangle, is equal to permutation of S0 n 1 m q to the inversion. But we know what this is in the previous theorem. Multinomial coefficient n plus m, n comma m. But of course, this is equal to the binomial coefficient. That's another proof of this. So in the previous proof, we proved this using induction, but now in this way, you can just prove this directly. Any question? A is a set, but set is a multiset. Yeah, A is a set, they're all distinct. But yeah, set is also a special case of a multiset. Did I answer your question? M is a multiset. Yeah, so we have multiplicities for the elements. Okay? If it's not clear, just please ask me. Multiset. The concept of multiset is we want to have repetition in your permutation. And in that case, we can also have inversion numbers, and it also has nice generating function, which is equal to the Q binomial coefficient. And that gives you another proof of the fact of this fact. All right, so we have defined inversion number of a permutation, or also a permutation of a multiset, which is often called multi-permutation, but yeah. All right. Now, what I'm going to do is this. I'm going to define the inversion number of a matrix. Let's see. Inversion number of a matrix. We will define this, which is consistent with the definition of an inversion of the inversion number for permutation. Permutation is a matrix, basically, if you consider the permutation matrix. So let's say pi is 1, 3, 5, 2, and 4, and this corresponds to a permutation matrix, say M. 1 in the first position, third position, fifth position, second position, fourth position. So this is the permutation matrix corresponding to this. So inversion of this is something like this, 3, 2. This is an example of an inversion. Okay? And let's look at the corresponding elements here. 3 is this, 2 is this. So this inversion corresponds to a pair of ones in this relative order. So here, inversion of pi corresponds to pair of, let's say, just a non-negative integer, non-zero element. Non-zero elements in this relative order. Right? Like this. They have to be in different columns and different rows. But one is to the northeast of the other. So for instance, how many pairs are there in this case? This and also, let's say, this and this. And also one more, this and this. There are three. There are three inversions. This, and this. They all correspond to this. So in this way, you can kind of see in a pictorial sense. So the inversion number, in this case, is equal to number of pairs of such, in this case. But they are all 1. So we can say sum of AB product, A located B, like that. Because AB are just ones. They are the same in this case. And actually, you don't have to say that they are non-zero even. It can be 0. For every pair in this position, you find all pairs of entries in AB like this, located like this. And then you add their product. This will give you the right inversion number for your permutation. Because if you select 0, then it will contribute nothing. If you select 1, 1 in this position, it will contribute 1, which is just a inversion, one inversion. Is this okay? Nice thing about this is that this can be defined for every matrix, not just permutation matrix. In this case, we don't really use that every column and row has exactly 1, 1. We don't have that thing. So this can be defined for every permutation. So that's the definition of the inversion number of a matrix. So let me define it in the next page. Doesn't have to be even a square matrix. So M is now just say any rectangular matrix. Entries in C. But yeah, let's first. The inversion number of M is defined to be A, B, so entries in M like this. A, B is northeast of A, and you multiply A, B. This can be defined for every matrix, not necessarily square. And under this definition, the permutation matrix gives you the same inversion number as the permutation. So let me give you an example. Let's look at just this alternating sign matrix, because it is a matrix. One, minus 1, 0, 0, 1. Doesn't have to be alternating for this step. It can be applied to every matrix, but let's look at this alternating sign matrix. What is the inversion number then? Yeah, of course, this is for every entries, but you can just look at non-zero entries, because 0, if one of them is 0, it will be 0. Okay, let's pick this one and then look at the things that are to the northeast of this. We have this thing over here, also over here. This will give you 1 plus 1. And for for this, okay, oh yeah, okay, let's go this way. For this, there is nothing over here. For this, there is one thing. It will be -1. And for this, there is how many? This thing and this thing. So +1, +1. Okay, for this, there's nothing above. For this, we have this one, so -1. For this, we have 1 and 1. +1, +1. For this, we have 1. Is this right? So the sum is, we can cancel these 2. We have 1, 2, 3, 4, 5. So the inversion number of this matrix is 5. So we define a statistic on matrices, which of course can be applied to the alternating sign matrices. I'm going to define one more very natural statistic on alternating sign matrix. Now, let's say B is an alternating sign matrix. N of B is the number of -1s in B. So, for instance, here, what is B of M of B? You just count number of -1s. 2. All right? So let me note this. For permutation matrix, we had nice formula for this. For alternating sign matrices, this has no known formula. Maybe it doesn't have nice product formula. But there is a nice formula for this. Q number of inversion. If we add something different, Q inverse of N of B has a nice product formula. As one of the homework problems, you will find a nice formula using SAGE. Any question? Okay. Yeah. So next time, next week, we will learn a very important lemma that I mentioned earlier, Gessel-Vienno-Lindström lemma, which is about expressing non-intersecting lattice paths as a determinant. And there's a very powerful tool, and we will use this to prove the generating function formula for the plane partitions. And this can be applied to many classes of plane partition, not just the ordinary one, but the symmetric plane partition, cyclically symmetric. There are many classes. There are 10 classes. Many of them can be applied, can be evaluated using this lemma. This is a very powerful tool, and it is used very, very often in combinatorics and also other areas. Okay, I will finish this today. Thank you for your attention.